And because of the nature of this class today, that we have two classes and there's lots of things happening, we might rush a little bit through it. So whatever's confusing you, I'll answer your questions on Wednesday. Although I also plan a quiz on Wednesday on exactly what we did today, to draw one logical circuit and add two numbers. So I will rush through introductory part, and then we'll do the real part a little more carefully. So what is this all about? So there are two parts. One, to make sure that everybody is comfortable with the number systems. So, usually we express numbers using base 10. So when we say that the number is 352, then each of the digits, besides reporting the value of the digit, has also something called place value. So what is this telling us? It's telling us that each of them is multiplied by appropriate power of 10. 2 not at all, to 10 to the 0. Then 5 is multiplied by 10, and 3 is multiplied by 10 squared. Is this how you read the value of a number? So that's called place value position. But now, and we use base 10 historically for many reasons, I'm not going to talk about it now, but people can use some other bases as well. So can we represent this number, 352, in the base 10? How would that number look in the base 8? What if for some reason I want to represent this number using powers of 8? Do you understand the question, what you want to do? So how would you do it then? I want to write it again, something like 8 cubed plus b times a squared. Why do I need 8 cubed? That's too much. That's 512. b times a squared plus c times. Sometimes really higher power shows up if you lower the base, but not this time, and it would be plus d. And then how do I come up with those digits? What do? I divide with the highest one. So I divide first 352 by 64. So what would that give me? 5. So 5, that would be what? 320, and the remainder is 32. So that tells me that I have 5 times 8 squared. And then yes?
Am I supposed to say base 10 or base 8?
No, it's 352 in base 10. So because how do you read 352? You must know. So this refers to base 10, and my result at the end will have label 8. Because if you, in the same line, if you have two different bases, you better make sure which base you are having in mind. So this meaning is 3 times 100 plus 5 times 10, and so on. And now it will come, yes. So it's 5 times 64. Now I'm going to take 32, and I will divide it by what? By 8. What would that be? 4 times 8, 32. No remainder. So it will be plus 4 times 8 and plus 0. Do you agree? So how do I write now this number? I write it 5, 4, 0 in base 8. So, or what if I want the other way around? 5, 4, 0, base 8 into base 10. What should I do then? Instead of dividing, I need to what? Multiply with the appropriate. So if I have 548, that's what? 5 times 8 squared plus 4 times 8 plus 0. And this is what? 352 base 10. Everybody okay with this? Yes?
How would you read that base 8 number in English? Like, how would you say it?
3, 5, 2, base, or 5, 4, 0, base 8. Don't read 300. Without those 100, just read the digits and say the base. And then the order said. So when you say 100, you are basically saying 10 squared. Although some people might be tempted, I don't like it, to say 0 on the last place, 4 on 8th place, and then 5 on 64th place, But there's no need for that because it's all nicely built in. And then you can use different bases. What if you use base 12? How would I express number 352 from base 10 in base 12? If your base is now too big, what do you need to do? To invent more symbols, because you need symbols all the way to the 11, do you agree? And they should be single symbols, not double symbols. So what do you have? Your digits are now 0, 1, and 9, and you need 2 more digits, and I'll use my initials, Z and P. So now we have 11 digits. I mean 12 digits, so 9th, 10th, and 11. And then what do? Then I'll take 352, I will divide it by what? 144, which is 12 squared. Of course, I do calculation in base 10 because that's what I'm trained to do, but I interpreted other bases. What would that be? 2, 288, 8 to 12, 4, 64. Am I correct with this? 12, yes. So now I'll take what? 64, and I will divide it by 12. That will give me 5, which is 60. And oh, how unlucky. I didn't need my digits. You see, the digits that I got are what? 2, 5, and the last one is what? 4. So this number is just 254 base what? Base 12. Let me make it a little bigger. What if it was at 7, 359 base 10, what would that be? Everything works the same way. I have 7 more here, so what will be my remainder?
Z.
11. No, my remainder is 11. Remember, 10 is Z. Remainder 11 is what? P. So it would be what? 25P base 12. Here it is. So as I said, because if you go below 10, you have enough. You even have extra digits that you don't need. But if you go above, you have to make a few more digits. Is everybody okay with this? Now what? For us, the most important base for what we are going to do today, which is circuits for addition, we are particularly interested in base 2. So then we want to write a number using powers of 2. So how do we do that? Let me look at one example. So here it is. I want 458 in base 2. And there are different ways. Unfortunately, what will happen when I write this 458 in base 2, number will get very, very long. Do you agree? Because the value is small, then I have quite many digits. So how do we do that? As I said, there are different algorithms. First, sometimes people want to determine lower digits, sometimes upper. But basically, here is what I would do. I would first decide what is the highest power that's below 458. Here are powers of 2. So 2 to the 1 is 2. 2 to the square is 4. Cube is 8. 16, 32, 64. 128, 256, 512. So what's the highest power below? 256, which is what? This is 2 to the 6, this is 2 to the 8. Agree? So this is what? 1 times 2 to the 8. So what would that be? So I'll have my digits. How many digits do I think do I need? 8 or 9? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. A little too much. Why? Because I have 2 to the 8, 2 to the 7, 2 to the 6, and the last one is 2 to the what? 0. So if I have 2 to the 8, and I do, because I'm above it, I have 1 here. Do you agree? So what do? Here I don't do division. Why? Because when you divide by certain number modular 2, you can either get a remainder 0 or 1. Do you agree? So that means you have it or you don't. If you have it, put 1. If you don't have it, put 0. So what would that be? 458. Does it have 256? Yes or no? Yes. Yes, subtract it. 458, subtract 256 and put 1. And what would that be? 20 what? 202. Do I have 128, yes or no? Which is the next one on the list. So this is okay. 128, the answer is yes. I subtract 128, and what do I get? 74. Is it correct? Please control my calculation. Yes. 74, do I have 64, yes or no? Yes. Yes, so I'll put 1 here, and I'll remove 64. And I'll get what? 10. Do I have 32?
No.
No, so I'll put 0. Do I have 16? No, I'll put 0. Do I have 8? Yes, I'll put 1 and subtract, and I get 2. So 8 is decided? Yes. Do I have 4? I don't. Do I have 2? Yes, I subtract 2. I get nothing. Do I have a remainder? No, here it is. So this is how you quickly switch a number from base 10 to base 2. Everybody comfortable? We'll do switching to base 2 quite quickly and quite often, so you need to be very comfortable with this procedure. And I said, to understand it and to be able to do it quickly and accurately. What if I want to go back? Then what do? I just go through the digits and then record the weights. So is this 2, yes or no? This is what? How many 4s? None. How many 8s? How many what? 16s, 32. This is what? 64. This is 128 and 256. And what do I do with these numbers? Just add them up, because you don't need to multiply. You're always multiplying by 1. So just record those where 1s are, and it will give you exactly this addition. Clear to everybody? All right. Then we can. So that's the first part of this story. So that is, you see. Oh, by the way, very often we just put the line above the number to make it sure that we understand that those are the digits of the number. And then what? Actually, it might be important here to talk quickly, at least, how do we perform addition and subtraction in some other bases. So let's say, let me subtract 1, 1, 0, 1, 0, minus 1, 1, 0, 1, base 2. By the way, we teach base 2 in the courses for future teachers. We have 2 of those courses here at Miracosta. And the reason is, how could you teach someone base 10 if you did it all your life? But when you teach kids, it's a new, base 10 is new for them. So we kind of put future teachers in the setting where they are uncomfortable in base 2, so that they understand how our operation really works without calling the habits. And I think that that's a very good idea. So here it is. So how do we subtract this? Basically, we subtract the same way as base 10, but we don't have a training. We have to think about the procedure more. So how does that work? Do we remember what happens? We subtract from the lowest digit, and then when there is enough, we kind of borrow, we say, although some professors disagree with the term borrow because we never return, so that's not borrowing. Basically, the term is trade. So do the trade of those bigger pieces into smaller pieces. Do you agree? So what would that be? Since I don't have enough, what do I need to do? Trade this 0, and now what? I cannot, like I say, 10, here I should call the whole block is how much? 2. But generally here it's much easier, because is that how when we borrow 10, and then we subtract from 10. Here it would be awkward to do it with 2. Usually what we do is the following. Here it is. When I borrowed, how much did I borrow? No, this is base 2. So I borrowed 2, agree? So 2 minus 1 will be what? 1. But generally what? You don't even need to do that. Whenever you borrow, your answer is 1. Why? Because you were subtracting 1, you didn't have enough. So you now have too much. The only possible answer is 1. So when you borrow, it's always 1. Here it is. So this is the guy. Now, what? 0 from 0, is that okay? Yes. Yes. 1 from 0, what do? You borrow cross here, and the answer is 1. Don't even worry what. Again, 1 from 0, you need to borrow, answer is 1. Here's the answer. So whenever you borrow, it's 1. It always means go to the opposite. So that's how this goes quickly, and actually it works just fine. Okay, now I will skip this part, read it from the notes. For example, here is octal expansion and all that. So there are little stories there. That's fairly easy. So I'd like to, so what is this, for example? Oh, let me show you just this example.
Question.
Yes.
I'm having trouble with the very first, like the farthest to the right digit. I understand that it's 2 and then 1, 4, 1, 8, but what is that very far to the right?
It's just whatever you see. You don't multiply at all, like in base 10. 735, it's 7 times 100 plus 3 times 10 plus 5 itself. Or if you want as powers, it would be 10 to the 0.
Okay.
And here, again, the same thing. So there's no enlarging. Those are just the pieces that you see.
Okay.
Because you see, what happens with the positional system is you count, but then you say, but I see three little marbles. But then you say, wait, which room is this? Is this simple room or more expensive or heavily expensive? Then that tells you how big those pieces are. So when you see the last room, what you see is what you get. No extra value factor, like in the other rooms. All right. Here is something that just talks a little bit about the economy. Let's say, they say, find the binary expansion of 7a, 3e in base 16. So number is by the way, this system is called hexadecimal. Hexa is 6. Decimal, so that's 16. So here's the number. So what's interesting in this problem, we usually communicate through base 10 because that's where our skills are. So if you want to go that way, I should go from base 16 to base 10, and then from base 10 to base 2. But here there is a shortcut. Why? Because you don't always have shortcut. Why do I have shortcut here?
15's power of 2.
Exactly. So what happens? Look at this. 7a, 3e in the base 16. So since 16 is power of 2, every block for 16 is how many blocks in base 2? 4, because it's 2. So generally, this e, which is what? Just one digit, will cover how many blocks? 4 blocks. These 3 will also cover 4 blocks. This a will cover 4 blocks. And 7 will cover 4 blocks. So instead of joining them and separating them back, I can actually just use individual representation. So for example, number 3, what is that in base 2? 0, 0, 1, 1. Do you agree with me? Because that's 2 and 1 is 3. What about number 7? So no 8s.
0, 1, 1, 1.
And no 8s, 1, 4, 1, 2, and 1, 4, and 2 is 6, and 1 is 7. And now what about A? What is A basically? Which number is that? 10. So you go 0, 9, and then A is 10, stands for 10, B for 11, C for 12, D for 13, E for 10, 11, 12, 13, 14, and F for 15. 1, 2, 3, 4, 5, 6 new digits. So E stands for what? I do communicate with base 10, but not globally, just on that low level. So here it is. So what is E? E is how much? 14. How much is 14? 14 is 8 yes, and then what? 4 yes, and 2 yes, and 1 no. So that would be what? 1, 1, 1, 0. So that's 14. And finally, how much is A? A is 10. What is 10? Yes 8, and a no 4, and yes 2. So that will be what? 1, 0, 1, 0. Here it is. Now when you join them together, then you will get the number. Why is that so? Because, with a little more explanation, this is like 0, this is 1 times 2, this is 1 times 2 squared, this is 1 times 2 cubed. And this is 1 times what? 2 to the 4th, 1 times 2 to the 5th, 1 times 2 to the 6th, 1 times 2 to the 7th. But in base 16, if I factor 2 to the 4th out, this looks the same way as this. And that's why that's important for base 16. So these are just below 16. This is 16 times a number k that's below 16. This is 16 squared times number L. This is 16 cubed times some number S. That's why that block analysis works. So that's between 2 and 16, who also communicates with 2 well. Which other base? 8. So 2, 8, 16 are bases that have that shortcut communication where you don't need completely to break it into base 10 and back, but you can do it in those segments. All right. Here is something that's very important for us, and that's where this story connects with what we do today. And what are these? These are very important circuits, and I really very often ask, even on the exam, just draw me full adder or half adder. So what are those? So it's very interesting how the concept of adding 2 numbers is designed. So generally, we needed to learn 2 things. We are adding numbers in binary system. So add numbers in a binary system, in the binary system. So here is what we want to accomplish, step by step. We are analyzing the following situation. How would you add this? 1.010101 and then 01011. Can we add these 2 binary, just, as humans? That means with little ideas and talk and extra, stories on side. What will we do? We say, how much is 1 and 1?
It's 0.
Because it's like 10. Do we reach the next level with 1 and 1? Yes or no? I cannot write 2. What's that? So it is already 2, but then we pack it in the next unit. So here's what I do. I leave 0, and I have 1 on the next unit. Do you agree? Like when you reach 10, you go to the next unit. By the way, this is the digit, and this is what we call carry on that 3rd line. What happens now? I add to those 2 1s and 0. So now I'm not adding 2 numbers. How many digits am I adding here on this level? 3. So how much is that? 1, 0, and 1. Do I stay below 2 or I reach next level? So that means I put a 0, and then I have another carry. Wow, forever. 1 and 1, do I have carry again? 0 and the carry again. 1 and 1, 0 and the carry again. 1 and 1, 0, and now there's only 1. Here is the addition. Whatever that is. Yes. Do we understand how this works? So we would like to make a circuit that does this. So generally, first, we want a circuit that does this line. That means we add 2 numbers. You see here, how many numbers am I adding here? Just 2 digits, do you agree? Because there was no carry in the beginning. So I want to learn first how to add 2 digits. And that's called half adder. So half adder tells you how to add 2 digits. So half adder. I want the circuit that does the following, whatever that half adder does. I want to feed it with 2 digits that are 0s or 1s, and produce how many outputs? One or two? Two. Why? Because I produce the digits, but at the same time I need to produce what? Carry. So I need to make procedure how to produce a carry and also how to produce the digit to print. So digit, the one that I get, I just say print, but the one that carries goes on the next line. So then what? I want to decide what do I need from this digit, and here it is. I'm not going to write it on the board. I hope it's okay. You can copy it from there. And here is what's happening. What happens when I add 0 and 0? Do I get 0? Do I have a carry or I don't? So here it is. I want something then on inputs 0 and 0 produces 0 on both carry. Here I called it sum. I better call it digit. What if I add 0 and 1? How much is the sum? So sum is 1. Do I have a carry or I don't? So no carry and the print 1. Agree? What if I have 1 and 0? Same thing. No carry and the print out 1. What if I add two ones? Carry 1 and the print out 0. Do you agree that this is what we want? My question is, can I make a circuit that does that? First, we can always make any circuit that does whatever you want. That's what we said a minute ago. But here I don't even need to go that far. I can recognize it easily. So what is the carry circuit? What's that? AND. And what is the sum circuit? Do you see that? Because look at this. Here it says 1 only if both ones. Is that AND? But what about this one? Says it's OR because B is true or A is true, but not both. Is that exclusive OR? And I told you I'll never use exclusive OR. This is the first time. We need it. So now, can we design a digit that does this? And that's what half adder is. Can we just do what we just said we'll do? So what is it? When I get my A and B, let's call them A and B, what should I do? To get carry, that's very easy. So what should I do? Connect them with AND and produce it out. Do you agree with me? And how do I produce the sum? Did we say exclusive OR?
A or B and not A and B.
Bravo. Do you agree with him? Or some people say just in your circuits class, they might say just, oh, I have a device for exclusive OR. Just call exclusive OR and connect it that way. No, in this class, we'll just build it carefully. So what would that be? I don't know, why did I go up there? It looks bad. So here it is. So what are we going to do? We'll take them, both of them, connect them with OR. And then what else? So this is A or B, and not both of them. So I can use this conjunction, but what do I need to do with it? To negate it. Here it is. And then I need more space. So here is negated conjunctions. Here is disjunction. So how do I connect them with what? And pull it out. That will give you the digit. Let me see, what is this? So it says A or B, and what? Negate, not both of them. Here is your digit. So this digit, this little device is called what? Half adder. Is everybody okay with this? So from now on, I will not draw half adder anymore. I'll just say, I use half adder. And that means I know what's inside. I'm not looking under the hood. I just label it half adder, and we know how to construct it. Is that clear? All right, that's good. But that will not serve me here on this line. Why? On this line, how many numbers do I need to add? 3. So that's what full adder does. it adds three numbers that are 0, 1, which are on, and off. Of course, you understand that here you are thinking when I feed 1, that means the signal is on, and when I feed 0, the signal is off. So what? Now we want the full adder. Well, let me just call the full adder and explain how it works. I hope I have it there.
I have a question.
Here it is. Yes.
For this thing, could you not just say the top part where it's if they're both and then carry, and then just say when not and then go digit?
No. I want both. I not when and not go digit. I want always both. So I want something on both of them. So I want to know, because this carry is connected to something later on. So I want to have that output for both. And not like if that not output this. Is that what you suggested, or maybe I missed something?
Yeah.
So generally, I want what? I want the gadget that has how many inputs? And how many outputs? 2. So I want always to know what's on both of them. All right. Now the question is, what if I have 3 digits? So now that's a full adder. I don't know. Don't I have a... it was too much to draw, it seems to me. Yes, I just told you the story. What say? No, did I draw it?
No.
Oh no, it's okay. Yeah. So here it is. No, I thought I drew it, but here it is. Now I'm having 3 inputs. Why am I having 3 inputs? Because at the end of the day, I might have carry already from here. I need three inputs. So what do we do with 3 inputs? You can never add 3 numbers. You always add 2 at a time. Do you agree? So what will I do? I will add A and B with half adder. What will that do? When I add A and B, I will have what? I will have the digit. I will have carry. And I have digit. And then what? That a digit, so you see, we are both in the lower room. Is this carry? So all these 3 are in the same room level, agree? Now, is this carry in the same room or in the next room? In the next room. So who needs to add up with C? Digit or the carry? Digit. So I take now C and the digit, and I also do half adder. So here is carry 1, let's say. And what will half adder do? Produces another carry and also produce a digit. Is that okay? And then what? This digit is exactly what my output is. So here's my final digit. So you see, this is digit 2, let's say, digit 2, mean from the second procedure. So there's carry 1, carry 2, and digit of the second procedure. The digit of the second procedure is my final result. Yes?
Wouldn't we add the first carry to the second part?
It'll come. That's the next thing. So digit 2 is just printed out, and that's it. Now I have these 2 carries. What do I do with them? They are both in the next room. Do you agree? So what happens? If one carry, so now comes a little tricky place where where we want to make sure that things are okay. If both carries are 0, what do I get? 0. If one is 1, 1 is 0, I want 1. Do you agree? What if they are both 1s? That will never happen. Why? Because, and that's a little tricky. Think about it if I don't convince you. If carry 1 is 1, if you remember when you have a carry, your digit is always 0 because you are exhausted. Because how do we get carry? 1 and 1, you get 2, your carry is 1, but your digit is what?
0.
So if you have carry on first, this digit is how much? Can you have carry on second? No, you are too exhausted from carry 1. So you never get on both of them 1. If your carry 1 is 1, your carry 2 must be what? 0. So how can I connect them then? There's no danger that they are both 1s. So what do I want? If one of them is 1, I'll just connect them with OR. So if they are both zeros, my carry will be 0. And if one of them is 1, carry will be 1. What if both of them are 1? That will not happen. Don't worry about it. Because I cannot have carry 2 now and go even to the other room. So if you have carries on 10s, that cannot produce carry on 100s. So that will never happen. So here it is. So if you connect this is called full adder. So now if I close what's under the hood, what is this doing? If I add 3 digits, it produces both carry and a digit. You print this, and you feed carry on the next line, and that's how you do addition. And what happens? If you use this circuit, you can add any 2 numbers. Because you just start with half adder, and then whatever produces on carry, you feed all these 3 on full adder, print, go on, and then you can write a little recursive program and finish all this. Are we okay with these 2 little gadgets? So as I said, I am rushing it a little bit today. Whatever we didn't cover in full detail, we'll talk about it next time. Here is something that now we want to use to actually represent not only positive numbers, but also to represent negative numbers. And that's a very interesting idea, but we cannot do very big numbers, and we also have a limited memory. So it's called 8-bit representation. Of course, you can get more 8-bit representation of integers. And those integers m are between 127 and negative 128. By the way, how many numbers are in this interval? 256. How much is 2 to the 8? 256. That's exactly, I'm using, with all possible combinations of zeros and 1, I exactly have space to present 256 numbers. But here is the story. Numbers between, suppose that my number is between 0 and 127. What can you tell me about this number? By the way, see, 8 is not easy, especially if you are in a hurry. It's a little hard to draw 8. I like to draw them in pairs, like this. There are 4 of those pairs. So these are 8 digits, and they are zeros and 1s. This is reserved. This is 1 if you are above 128. But is my number above 128? No. So all my numbers will start with what? So for example, if my number is 100, so 100 in base 10, how much is that in base 2? I go 128 and what? 64, 32, 16, 8, 4, 2, 1. So 128, no. 64, what? Yes, 1. Then 36 is left. On 32, what? 1 and 4 is left. No here, no here. 1, 4, and 0, 0. So here it is. 110 would be what? It would be 0, 1, 1, 0, 0, 1, 0, 0. Is that okay with everybody? But then what? Why do I need that 8 digits if it's always 0? And here is something very interesting. I will use a 1 to present negative numbers. Why is that so ingenious? Because you see, when you have a circuit, it's either yes or no. Do you agree? So if you don't have it, it's 0. If you have it, it's 1. But you cannot represent -1, like I owe a signal. So generally, they wanted a way to code the negatives, and then in that coded with positive mass. But generally what? Whenever you see that the number starts with 1, so for example, let's see what is the number. So how do you interpret the number? Like this, 1, 1. Let's see a number like this. Yes, that's the number 255. Represents 255. So how do we decide which number to represent? It is actually what? But we want, instead of 255, actually to represent, we don't care about the big numbers, because we said we only care about numbers up to what? 127. I want this number, instead of that, to represent